Okay, perfect. So yeah, thank you very much for the quick introduction. My name is Johannes Flotzinger, and tonight, or maybe this morning, I'm allowed to talk a little bit about my topic, which is the basis of my research. And the talk is called Bridging the Gap, Advancing Civil Engineering Inspections with Computer Vision. But before, maybe a few words from my side. Yeah, I'm basically a civil engineer. That's what I've studied. Then I started some research at a different university about the field of building materials. And I did a lot of studies in the field of building materials, rehabilitation and building defects, and also concrete, the rheology of concrete. And yeah, since 3 years now, I'm a PhD student in Munich, and my research topic is the automated bridge defect recognition, where I'm also part of the DACLI squad. And the DACLI, as you maybe have already recognized, in the top right corner of the presentation, there's a logo, and this is a DACLI, which is a dog. It's also called Dachshund, sausage dog, or wiener dog. So it's our mascot, basically. And quick spoiler in advance, we will host a challenge on a data set at the WACV 2024. But later on, I will say a little bit more about that data set. So our menu is basically a few definitions, the motivation behind my talk today, a few words about the digitized visual inspection, some preliminary work we did, and the main part is the DACLI 10K dataset, which is currently the biggest and most granular dataset for bridge damage segmentation. And in the end, I will talk a little bit about our workshop at WACV and the challenge. So first of all, maybe a quick explanation what civil engineering structures are. Civil engineering structures are designed by structural engineers, and their design must ensure the load bearing as well as economical and safety concerns during their working life. And neither the parameters with respect to loading nor materials are fully known. So basically, the design works based on probabilities. So for example, with 95%, we can say that the concrete has a compression strength of at least the value that is given. So we have uncertainties in the behavior of the structure even after planning, and most of them are made of concrete or steel. They are crucial elements of the public infrastructure, and these structures must operate technically faultlessly, and their maintenance measures must be well planned. They enable transportation, water supply, energy supply, and the wastewater management as displayed in the images. And a failure of individual structures results in enormous costs and can be dangerous. So our infrastructure has a problem. On the left side, you can see the average age of infrastructure types in blue and their minimal design lifetime in the US in 2022. Nearly all infrastructure types reach the end of their lifetime, as you can see, in the near future. So with growing age, also, it is more likely that defects occur. And thus, frequent high-quality inspections of the infrastructure are indispensable, especially for the ideal planning of maintenance measures, because there is a sweet spot for restoration works, depending on the life cycle of the structure, and the avoidance of unnecessary closures, as well as to prevent the structure from abrupt failure, of course. And at the same time, we want to minimize the burden on the economy and the population as a result of blockings during inspections or maintenance measures. On the right side, you can see the number of bridges in need of replacement or rehabilitation in the US from 2019 to 2023 in thousands. So you can see that in 2023, there are approximately 222,000 bridges in need of replacement or rehabilitation. In other words, 1 out of 3 US bridges needs to be replaced or repaired. At the current pace, it would take nearly 75 years to repair them all. And additionally, the financial costs are enormous. So in general, for instance, furthermore, for instance, in the US between 2020 and 2029, approximately $2.8 trillion of the transportation infrastructure are needed. but only $1.6 trillion are funded, leading to a funding gap of $1.2 trillion. And according to a 2022 survey in the European Union and United States, infrastructure firms noted that the availability of skilled staff is one of the biggest barriers to their infrastructure investments. So what can we do about it? First of all, well, what I can do, and based on my research, what I can offer is to make the inspection process more efficient, consistent, and safer by using computer vision for the automated damage recognition. Thus, tackle the problem of staff shortage and costs for inspections, and maybe enable more frequent inspections, leading to more confidence in the building assessment, and eventually extend working life of the structure. So in the following, I will describe the problem of visual structural inspection using a bridge inspection as an example. As most of the civil engineering structures are inspected analogously, this problem description for bridges can be projected on any other building type, so also on power plants, dams, pipelines, sewers, and so on. Additionally, it is important to note that the majority of civil engineering structures is made of concrete. For example, in the case of bridges, there are 90% of them made of concrete. The defect classes also in our dataset that I will describe later on have a very similar visual appearance on other concrete building types. Therefore, it is very likely, without having tested it yet, that the models also work on other concrete building types. So you can see here a image of a bridge inspection with a mobile under bridge inspection unit. And on the right side, you can see a damage sketch. The currently practiced bridge inspections are carried out by professionally trained civil engineers, also called bridge inspectors. And usually the inspector observes the complete surface of the given building while capturing each defect. During inspections, it is mandatory to detect visually recognizable defects. And after the detection of a defect, the inspector takes an image and notes the damage class, size, and location in a handwritten damage sketch as shown on the right side. So a damage sketch, or this damage sketch in particular shows a 3 T-beam cross-section, and it's basically represents the bridge flipped open along its longitudinal axis. So you can see here the vertical lines here, they represent the edges of the cross-section shown here. And you can see that the defects are numbered in chronological order. For instance, we have here the number 32. And number 32 basically says there is a crack or multiple cracks with a crack width, so a width smaller than 0.2 millimeters. So this process basically is repeated for each defect. And after the inspection was completed, some inspectors additionally transferred the handwritten sketch to a CAD sketch. And finally, the assessment of the building is determined by calculating the condition grade, which is similar to grades in school. And he prepares she prepares the inspection report. And in the inspection report, all defects are listed, including their grades and recommendations regarding restoration, traffic load limitations, or building a new construction, which can also be one case. And furthermore, the defect sketch is attached to the report in order to enable a visual comparison with other, especially consecutive inspections. The defect sketch is the basis for tracking the defect development, but the problem is that the condition ratings, which are strongly based on the damage sketch, they tend to diverge and they are quite inconsistent. And the main reason for that is the variability in inspection documentation. For example, in the field inspection notes and the photographs, for example, some inspectors likely take more images, more notes, the others less, and so on. And the inspection notes concerning important structural defects or corresponding photographs are even often omitted. The correct image must be found for the corresponding defect, which is also an issue because they might get mixed up. And the damage size is measured usually with a pocket rule. thus it's imprecise, and the damage localization is often estimated or determined by measuring the distance to the next bridge pillar, which is also inaccurate or even impossible on bridges with a big span. So the current defect documentation is often inconsistent, error-prone, and lengthy. And the currently practiced analog inspection process makes it difficult to guarantee frequent and detailed inspections. And we want to make a contribution to a digital inspection for structures being more efficient. Yeah, so how do we imagine the process of visual bridge inspections? The digitized inspection, how we define it, is structured as follows. First of all, we generate a building information model, which is displayed on the most left side. The building information model basically is a 3D model of the according building. And it also has some metadata, like the building material, the age, the kind of concrete, for example, and so on. And then when there is a inspection needed, we go on site and basically automatically get all info for each defect, meaning we collect each damage regarding its class, its measurement, and its localization. And this so-called damage info can then be fused with the building information model. And so we have a kind of digital twin. And my main work is the middle process, the defect recognition, or rather generating the damage info. And the damage recognition models then can, of course, be deployed on any device, for example, smartphones, drones, robots, and so on. And this digitizing of the inspection process, especially the gathering damage info, automatically will make it more efficient, more consistent, safer. And there is also maybe no blocking of lanes necessary if there are UAVs used. All right, so maybe more in detail, the task that we try to solve is the defect recognition. So basically make the left image to the right image. So we have here a defect, which is called spalling with exposed reinforcement, and there's also corrosion on the exposed reinforcement. And we want to semantically segment this defect. We also want to measure it. For instance, this one has approximately an area of 0.5 square meters and a depth of 5 centimeters. And we also want to localize each defect in the WGS 84 with a latitude, longitude, and altitude. And that informations are our damage info, basically, and that's what we want to gather. Yeah, and furthermore, the models we develop must be robust. They should work on data from smartphones, tablets, smart glasses, UAVs, and they should be robust against varying camera poses and environmental conditions, which is also strongly varying on site. So in the following, I will explain to you how we tackle the problem, advancing civil engineering inspections with computer vision, starting with the preliminary work. The preliminary work was the basis for the decision to make our own dataset DACL10K. So when I started my research, only one multi-label classification dataset existed, and there were no semantic segmentation datasets. So we developed multi-label classifiers for defects that commonly occur on concrete structures. Thus, we could classify defects on images non-mutually exclusive. And at that early stage, we realized that we have to bring our civil engineering problem to the computer vision community. So we did some cleaning of the datasets that included obvious false labels, and we also added consistent data splits to the according datasets if there were no consistent splits already, because this was not the case for every dataset. Then we thought, okay, we cleaned our data, we did consistent data splits, so people could use it now, but nobody knew about it. So we asked ourselves, how can we maybe push it? Then we developed ByKit, which is the acronym for Building Inspection Toolkit, and ByKit is a Python API, which enables easy access to all relevant datasets in the field of damage recognition on civil engineering structures. And Bikit currently offers 10 datasets of this domain. We offer consistent splits, as already mentioned, and via Bikit, we also provide our pre-trained models and the models of people that submitted results to Duckly AI. And Duckly AI is, there's a screenshot shown on the right side. Duckly AI is a website, and it's basically the platform for damage recognition enthusiasts and brings together practitioners and researchers. It's basically a leaderboard that shows the best performing models on the given data sets. Currently, there are 2 data sets in Duckly AI, so you can see the performance of different submitters on that data sets. And we also directly link the source code there. So it's, yeah, that's what Duckly AI basically is. And what did we next? We made a small multi-label dataset for defects occurring on concrete structures called Duckly 1K, but sourced from real-world data, meaning that we gathered data from civil engineering offices and authorities. So the images we gathered are real inspection images. So that's the kind of data that inspectors produce on site. And we combined multiple open source concrete defect datasets in so-called metadata sets. There was, for example, a multi-label dataset, a multi-class dataset, and 2 binary cracked datasets. And so we did different combinations of that datasets in order to get the most or the best performance on our real-world dataset called Duckly 1K. We also tried to push performance with heavy data augmentation, varied training and test resolution of the images, applied oversampling to tackle the problem of class imbalance. But in the end, the performance was quite bad. So what we also maybe recognized or realized maybe again was that we additionally need more info than the damage class. So we also need the size and the localization of the defects, at least on a pixel level. So we decided to do our own semantic segmentation dataset called Duckly 10K. What is Duckly 10K? Duckly 10K is a multi-label semantic segmentation dataset for bridge defects and bridge components. That means we have 19 different classes in total. We have 13 defects and 6 bridge components. And these 19 classes are pivotal in assessing the structural integrity of bridges and guiding decisions, such as already mentioned, restoration efforts, traffic load restrictions, or even bridge closures. I would show one example here in the middle, that one. So we have here multiple small cavities in pale purple. Maybe I grab the laser pointer, 1 second. Yeah. You can see in pale purple the cavities, which are basically air bubbles that remained in the concrete after hardening. So that's a defect. Then we have a hollow area, meaning that there is a hollow concrete, but yeah, we can only analyze it visually, of course. So we don't recognize the hollow area itself, but indirectly we recognize it still, because usually inspectors, when they see when they detect a hollow area, they mark it with chalk, and that's what we recognize here. Then in turquoise, we have a spalling, so spalled concrete, and we have some exposed reinforcement bars here in also in deep purple, and we have rust, which is displayed in red. So that's how our data set looks like. What was our approach? We basically took the German standard for inspections, but I should mention here that the defects worldwide on concrete structures also look very familiar. So it's not only for German standard, it's of course probably for every standard in the world. And we try to find all defects in the standard that are visually distinguishable. So they are unique in their shape and unique in their texture, or unique in their texture. And also what we have to take into account was what can we expect the annotators to annotate? Because these are not objects from our daily lives. So I guess not many people are familiar with concrete defects, and also some of them look quite similar. So differentiating between them is hard for people that are not confronted in their daily lives with concrete defects. Yeah, but that was the selection basically that we took, and we also trained some baseline results on our DACL10K dataset. Our main metric is the mean intersection over union, and that is reported here in this table. We analyzed 3 architectures. The first one was DeepLab version 3+, then a feature pyramid network, and we combined both architectures with 3 encoders with MobileNet version 3 large, EfficientNet B2, and EfficientNet B4. And for both architectures, we investigated the auxiliary loss, so with and without auxiliary loss, as you can see here in the rows. And additionally, we analyzed a transformer-based architecture, a segformer model. And the best performance was obtained by the feature pyramid network, as you can see, in combination with the EfficientNet B4 encoder, with a mean intersection over union of 0.41. But we also did a qualitative evaluation, especially suited for practitioners. We asked 5 civil engineers to annotate 4 representative images from the DACL10K test split. We told them to annotate the images with the same granularity they would expect a software to highlight the defects for them, which is the practical evaluation, especially useful for practitioners, as already said. And it's the comparison of the model's performance with the engineer's expectation. So I want to focus on these 3 samples and the comparison between Engineer 5 and the machine, because Engineer 5 was the one who expected the most accurate prediction. So I quickly transposed it. So you can see here in the first row, the annotation of the best engineer, so to say, and in the bottom row, the prediction of our model, of our best model. You can see here the first sample was predicted quite well. I would say there is not much difference. Even the prediction of the model is a little bit more accurate. The second image is a spalling with exposed reinforcement, rust, and some cavities. The cavities were not classified by our model, so they were forgotten. And on the third image, you can see a more complicated sample, because there are more defects. Also, the resolution wasn't very good. So what do we have here? You can see here in green some weathering. So that means basically, weathered concrete surface. There may be some moss or dirt or dust. Anyway, that was not recognized by our model, but our model did recognize here, marked in blue, the wet spot. That was quite well. What it didn't recognize was the rest formwork. The rest formwork is here marked in yellow. Rest formwork is or has to be removed after the hardening of the concrete. If not, there might be issues with the drainage of the water on the bridge. So this is a very likely damage cause later on. So it was not predicted by our model. Our model did predict the big rust stain here, which was also, of course, recognized by the engineer, but he also annotated some small rust stain points, which were not all recognized by our model. We have some spallings over here, which were not recognized by our model, but our model recognized the drainage pipe here on the right side correctly. So yeah, that's basically what the qualitative evaluation showed. All right. So what challenges do we have in our data set? You can see here, I take the laser pointer again, sorry. In the first row, there are 3 images and all of them show a crack. But on the most left side, you can see that there are 2 different, completely different surfaces of concrete. On the left side of this abutment wall, you can see the crack on very clean gray concrete. On the right side, you can see it on heavily weathered concrete. So sometimes the background of our objects immediately changes in one image. On the second image, you can see a thin crack at a graffiti wall, which also is quite challenging. And on the right side, you can see a crack, and in front of the crack, there is a lot of vegetation. Then I also want to show you the last row. You can see here 3 different defect types. On the most left side, you can see spalling. In the middle row, you can see rock pocket. And on the most right side, you can see washout concrete corrosion. And all textures of these defects look similar, which also makes it very, very challenging for our model to detect these defects. But it is important to differ between them because their assessment has a big impact on the final condition rating. All right, then on the right side, you can see class-independent challenges of our data set. So in the first row, the top row, you can see on the most left side a rust stain, and the rust stain slowly vanishes when you come to the outside of the polygon. So it's hard to say where is the border, where does the defect end, and this is especially hard for people that are not familiar with concrete defects or inspectors. But I should also add that each inspector also has his own opinion on this, where a defect ends. So yeah, that's a ambiguous problem in the data set. On the second image, you can see a slowly disappearing protective equipment. So it gets lost in the background somehow. On the most right side, you can see many defects overlapping with each other, which is also very common in our data set. On the most left side in the bottom row, you can see some overexposure in our image. You can see people using flashlights for the inspection. And on the most right side in the bottom row, you can see also some partially reflections in the image. All right, that are the challenges, and that's what, or a few examples that show the challenges of our data. All right, so now I'd like to highlight our workshop and our challenge. We organized the first workshop on vision-based structural inspections in civil engineering at the WACV 2024. And we will host the Duckling Challenge within the workshop. The workshop focuses on damage classification in the field of civil engineering using computer vision, inviting experts from the civil engineering domain and other fields who face the problem of visual defect recognition. And the central part of our workshop is the Duckling Challenge on the Duckling 10K dataset, of course. And there's still plenty of time left for training models. To be exact, you have 29 days, 17 hours, and now 21 minutes, I guess, left to train your model. Just scan the QR code on the right side to get to the challenge website. We include prize money. We include prize money. In total, we have $6,500. So how do we bridge the gap, as the title promised? We bring our civil engineering problem to the computer vision community. We make clear that visual inspections of civil engineering structures are important due to the aging infrastructure stock. And we aim to improve the current inspection process by using computer vision models for damage recognition. We open source our data and models. And in the end, we organize a workshop and host a challenge on Duckling 10K, our dataset, which is currently the biggest and most granular dataset for bridge damage recognition worldwide. So my references, thank you very much for having me. It was a pleasure. You can see here also of course, I have to highlight that. You can see a link to 51. Our dataset is already integrated here. So just make sure to, use this URL, check out our dataset, participate in the challenge, and maybe we will see at WACV. Thanks.
All right, it looks like you do have 3 questions in the Q&A, and I think what may help is that the context for them was around slide 16 is when the questions were being asked.
Yes, sure. Sorry. All right. Why wet spot and weathering are having same color branding? Is it being considered as same? No, wet spot and weathering are 2 different. They are not defects itself, but they are important for the inspection. Weathering is supposed to be green in dark green, and the wet spot is supposed to be a more blue greenish. It's hard to differ. I'm sorry. The most color palettes that I found have a limit of 12. Yeah, we will have to maybe choose a better, more differing color set. Sorry. So they're not the same. Similarly for bearing, drainage, and tape. Yeah, they are also supposed to be different. Bearing should be brown, drainage should be dark red, and tape, joint tape should be purple. Okay. Are these segmented or human-made annotations? Thank you very much for the question. And yeah, thank you also to you for your question, Raj. Yeah, well, all our annotations are by humans. Half of them was made with civil engineering students that were supervised by me, and the other half was annotated by a professional annotation team.